Thank you very much for staying until the very end. So I'm going to talk about a fancy physico-chemical system which was brought to my attention 10 or 11 years ago by a colleague in Toulouse, Véronique Pimienta, who is a chemist. And she came to my office and she brought a lot of pictures and videos, etc., etc. And she said, well, this is what I've observed, and I'm looking for somebody who would be able to explain what's going on in the system. Would you be interested? And unfortunately, I said yes. And that was the very beginning of a series of nightmares, which are not totally finished today. But there was also the beginning of a great fun, I would say. So I'm going to try to explain you what's going on in the system. And so it's apparently a very simple system. So you have a petri dish with water in it, and you just release a drop of dichloromethane. So dichloromethane is an oil, basically, with a certain number of specific properties. For instance, it's very volatile because it boils at nearly 40 Celsius. It's also heavier than water, which means that actually the drop here is a little bit plunging into water. And it's also very weakly viscous and slightly soluble in water. But the main thing here will be that it boils at almost 40 degrees. Okay, and to this, you add a very specific surfactant whose full name is written here. I will not try to pronounce the name, so let's call it CTAB. And you can add this surfactant either only within the drop or only within the water or both. And when you do that, you observe. No, by the way, I would say that what I'm going to describe and talk about is actually a specific system which belongs to the much larger family of chemical oscillating systems. And the best known of them is, of course, the Belousov-Sabotinsky reaction. So it's the same broad family. Okay, so for instance, here is a phase diagram of what you can observe when you increase the surfactant concentration in that system. So at low concentration, you can observe this kind of evolution. I will show you movies in a second. But as you increase the concentration, you can, for instance, observe rotating drops like this, or drops developing kinks, which emit droplets, etc., etc. So you will see how it looks like. So let's play the videos. So that's the smallest. So we are looking at the drop from the top. So this is the drop, and you see that this drop is emitting tiny droplets all the time. So now we increase a little bit the concentration of surfactant. So, by the way, in 4 cases, surfactant is distributed within both the drop and the substrate. Okay? So here you see that the drop is pulsating very regularly, and it emits rings of droplets. So this is almost the critical cellular bicellular concentration, but if we go well beyond that, we get this nicely rotating drop, which emits droplets by the 2 tips, you see, and increasing again. So you see for the highest concentration here what happens. So the drop develops into an hexagonal or pentagonal shape, and from time to time it emits droplets by the tips. Okay, so it is this kind of system in which we are interested. We recently published a paper on the specific case of the rotating drop, but I will not elaborate on this. Actually, I will concentrate on a very specific case, which is the one in which we introduce the surfactant in both phases at a specific concentration, which is half a millimolar pulse. Okay, and in this case, here is what you observe. Be patient, okay? Okay, so this was the kind of video that Veronique brought to me and said, well, please explain. Okay? Okay, so I tried my best. And so if we look again at this fancy droplet, we can of course record easily the variation of the droplet radius here, or at least what we see at the surface, at the free surface, because we know that of course there is a major part of the droplet which is below the surface and we don't see it. But we can record the evolution of this radius here, as well as that of the radius here of the rim we see. And if we concentrate on that one, for instance, you see this record, and you see that basically the amplitude of the oscillations of the rim radius are a few millimeters, here 3 to 4 millimeters, whereas the drop itself is 3 millimeters in diameter. So these are really huge pulsations. And apparently, these are the largest that have been observed with these physico-chemical systems. So, of course, now comes the hard part of the job, at least for me. How can we rationalize what we see in this video? So, I will only touch every mechanism we have been able to explain more or less. I will not go into much details due to the lack of time. But I will try to explain what I think we have understood nowadays. Okay, the first thing, of course, is to explain why the drop first spreads on the surface. Okay, so this is quite classical, actually. So we have a film forming around the drop, and of course, the evolution of this film is governed by what happened at the leading edge. And so this is well known. So basically there is surface tension at the water surface pulling the film outwards. And there are the other two tensions, the one between the oil, so the dichloromethane, and the air, and that at the interface between dichloromethane and water, trying to pull it inward. And of course, as is well known, the film will spread if this quantity, which is known as the spreading parameter, is positive. And here, with what we have, that is with the values of we have, and you will note that actually the surface tension of water is well below the usual one because of the presence of the surfactant. Actually, with these three values, the spreading coefficient is indeed positive, and so we expect the drop to spread, of course. But then, of course, we can go one step further and try to understand the evolution of the spreading process. And for this, actually, we can consider that the drop is actually feeding the film around it, and so it's a point source. So and this is almost a 2D problem. So basically, the radial velocity within the film takes this form. So r is the radius of the drop, and this is dr over dt, of course. So there is a 1 over r radial velocity in the film, and the driving force at the front is the spreading coefficient times the perimeter of the film, of course. And so this is what drives the spreading, and what resists the spreading, of course, is the viscous force below the drop. And because the film is spreading, there is a boundary layer developing over time at the water-oil interface. And well, this boundary layer, of course, evolves as the square root of time. And if you write down the stress at every radial position below the film, and if you integrate that across over the drop surface, then balancing the two forces, you end up with this differential equation, which tells you how the radius of the film evolves. So, integrating this equation, you end up with the conclusion that the film should spread as time to the power 3/4, and this is a well-known spreading law. But if we compare this prediction with our observations here, you see that the agreement is not very nice, because during the first pulsation you saw, actually, well, the exponent of the power law is close to 1.1, and then as time evolves, for instance, during the fourth pulsation, there are two stages. In the first stage, the exponent again is larger than 1, it's close to 1.2, and it's only in a second substage, let's say, that the exponent decreases and is close to 0.8, which is not so far from the 3/4. So what happens here? So this is where we have to consider the surfactant in more detail, because actually this is the initial situation, so there is surfactant uniformly distributed at the surface of water, and then we release the water at the surface. But it turns out that actually the area required by one molecule of surfactant is not the same at the surface of water as it is at the interface between water and oil. The surfactant needs a larger area here, which means that when you release a drop, actually surfactant is moving outwards and it tends to accumulate here around the drop. Okay? Which means that actually here the surface tension of water is smaller, well, it's lower than what we predicted previously. And for this reason, actually, the spreading coefficient is not uniform, and actually it evolves with time. And so, well, considering the desorption process, for instance, you can end up with a simple model of evolution of the spreading coefficient, which basically, let's say, a constant value plus a term which, over a certain interval of time, grows linearly in time. Okay, and with this, actually, if you go back to the differential equation I showed before, you end up with this evolution for the radius of the fin, and you see that there are now two terms, and of course, depending on which time interval you are considering, one term will win over the other. Yes, Stefan. Okay, so, but the main effect is that in this stage, okay, so with this, actually, well, you can, of course, consider what happens at the very beginning of the release, and then one term, the term which is related to desorption dominates, and you have to conclude that the radius grows as time to the power 5/4, not 3/4. Okay, so it means that this is a super spreading regime, and this is not far from what we observed. So we were quite satisfied with this. And of course, as soon as desorption is completed, then, well, the spreading coefficient recovers a quite constant value. And for this reason, we recover the classical spreading law with T to the 3/4. So this seems to be quite consistent with the observations, and so we were quite happy with that. Okay, so that's for spreading, which is the easiest part. So now the main player in the system actually is the evaporation that takes place at the surface of the film. Because keep in mind that dichloromethane is very volatile and is boiling at about 40 Celsius. So evaporation is really strong in the system. And actually we measured Veronique measured the evaporation rate. That is, she placed the Petri dish on a precision balance, and she measured the evolution of the mass on the balance as a function of time. And she did that, of course, for different drop sizes and for different sizes of the Petri dish. And so you see that there is a first stage in which the mass decreases linearly over time. So this gives you a good estimate of dm over dt, of course, and you can reproduce this in, you can change the size of the drop in a given Petri dish, and you can change the size of the Petri dish. And you see that in each series of experiments, there are two stages. That is, increasing the volume of the drop first increases the slope. And of course, this is what you expect because there is more dichloromethane in the system, and so evaporation is stronger. But at some point, actually, the size of the drop doesn't matter anymore. And this is actually because the drop is large enough for the precursor film, which is ahead of the big film you see on the movies. The precursor film actually has reached the lateral boundary of the Petri dish. So as soon as this happens, you can increase the size of the drop. You don't change the evaporation rate because the whole surface is covered by dichloromethane. Okay? So the surface is saturated. And of course, the larger the Petri dish you take, the larger the evaporation rate is. And you can plot these three values here as a function of the area of the surface. And this gives you, actually, once you normalize it by the area, this gives you an estimate of the evaporation flux. So once you multiply this by the latent heat, then you get an evaluation of the heat flux, which is evaporated. And this quantity here will be very important for the model I will show later. Because, of course, the first thing is to have an idea of the temperature distribution within the film. And since we didn't have an infrared camera or something like that to measure temperature distribution within the film, we had to elaborate a model for this. And so, of course, we have to make crude assumptions. The first of them was that the film has a uniform thickness. Then we consider that the drop is a reservoir that feeds the film at a constant flow rate, which means that this quantity here is constant. And then, of course, we assume that the radius of the film evolves as a certain power law of time. You saw the two exponents we were able to derive. And so with this, actually, we have this velocity field, with this velocity field within the film. And then we make classical assumptions that is only the radial velocity is important regarding advection, and only diffusion in the vertical direction is important. So with this, actually, you end up with this expression for the temperature field. So you see that there is a minus sign here. Of course, temperature is decreasing from the drop edge to the edge of the film. And of course, it's decreasing also from the bottom to the top of the film. And all these coefficients, we can measure them because we know R of t, we know the derivative, we know the power law for the evolution of the film size. We know now the evaporation flux, so we can play with this distribution. And so playing with this distribution means in particular that we can evaluate the temperature gradient at the surface, and with this, we can determine the strength of the Marangoni effect. Okay, so the Marangoni effect actually, or let's say the radial derivative of the surface tension is given by this expression in which we can measure everything. And the rest are just physical properties of the system, okay? And so because of this positive radial gradient of surface tension, there is an outward Marangoni flow which is required in order to satisfy the shear stress continuity at the surface. And this shear stress, of course, induces a flow within the film. And this flow actually has a very simple form. It's a Couette flow, basically, except that it's not a classical Couette flow because you see that actually, well, there is, of course, a linear dependence with respect to z, but there is also a linear dependence with respect to the radius, which comes from actually the fact that the gradient of the surface tension also depends linearly on the radial distance. But anyway, there is a quad flow driving the film outwards due to evaporation and marangoni. Sure.
If you have a temperature gradient, then the local evaporative flux is also different.
Yeah, and this, for sure, yes, but this is an excellent question, and no, because we were unable to measure the local evaporation flux. So this is a very crude assumption we make to consider the evaporation flux as uniform. This is an excellent point. Yeah, we have been unable to go beyond that for experimental results for the time being. But I fully agree with your point. Okay, so yes, so we have now this marangoni flow, and of course, remember that there is fresh water around, and the question also is how the marangoni flow meets the freshwater surface. Because of course, at the edge of the film, we have a certain shear stress at the surface, which is balanced by the marangoni flow. But at the water surface, beyond the edge of the film, of course, the surface tension is uniform, and so there is no shear stress. So how do you reconcile the two? The answer is that actually the rim you see in this picture is a structure that is able to reconcile the two. And you will see in a minute why. Okay, I will skip this one. Okay, so the rim is this. The rim is just the fact that the height of the film is non-uniform near the edge, and that there is this bump here. And so if there is a bump, so that is if the film height is non-uniform, then you can estimate that the pressure within this region is given by this hydrostatic component plus the capillary component. This pressure gradient being this pressure being non-uniform, it has a radial gradient. This radial gradient induces a Poiseuille flow in this region here, actually a semi-Poiseuille flow, because of course there is the boundary condition at the surface implies that the velocity profile has this form here. If we assume no shear at the surface here, and of course we have to enforce the fact that no fluid must accumulate at the leading edge. That is, we have to balance the marangoni flow within the film with this Poiseuille flow within the rim. And so, expliciting this condition actually, and noting that actually what is the dominant term in the pressure gradient is a term that results from the third derivative of the height, because if you differentiate the pressure here, you see that you can get a third derivative of h. So if we consider that this is the dominant term, and it can be proven, by the way, actually you end up with the fact that the Poiseuille flow that is able to cancel the marangoni flow has this property, that is, this equation determines, actually, if you want, it determines the width of the rim, or if you know, and this is the case, if you know the width of the rim experimentally, it determines the height of the film. So this was actually one of the important conclusions we got, because since we know the average evaporation flux, since we know the evolution of the radius of the film, and we know also the width of the rim, then we can have an estimate for the height of the film. And with this condition, actually, we estimated that the height of the film just ahead of the rim is about 3 micrometers, which is reasonable, but this is a quantity to which we don't have access, since we just have top views of the system. But yes, of course, the size of the rim, we know it, and so because of this condition, actually, we were able to estimate the height of the field. So that's what I wanted to say regarding the... Yeah, no, there is no Taylor-Click dynamics here. I will show what happens to the rim in the next slides. But no, it's just a balance in order for no fluid to accumulate at the rim. It's the only criterion we involve. Okay, so what happens to the rim now? So let's play again here. So you see the rim propagating outwards. You see here that a disturbance starts to form. Sorry, or maybe it's better to look at it with this four views here. So that was the point I reached on the video. So you see what happens in the next few instants of time. So clearly, well, the rim is destabilized. There are droplets forming on the rim, and well, a few milliseconds after that, the whole rim will be made of collection of droplets. Okay, and of course, the question is, what is the instability at play in the system? Is it something like Rayleigh plateau? Is it something else, etc., etc.? And of course, since we just have images taken from the top, we don't have many, let's say, many indicators to test which kind of scenario is taking place. So we had to, again, to make some assumptions, etc. And actually, what is important also is to consider, well, the differences which we have with the classical Rayleigh plateau system, because in a classical Rayleigh plateau instability, of course, you have a thread with a constant diameter, and so there is a most amplified wave number, which is about 9 times the thread radius. And here, of course, the situation is more complex because there is a radial flow, so the length of the rim is increasing over time, the diameter of the rim is decreasing, so everything is evolving. So how can we combine that to check whether or not what we see is a Rayleigh plateau? Okay, so actually, if you really look at the evolution of the size of the rim, you see that there are 2 stages. There is the first stage in which the size of the rim is increasing up to a maximum, and then it decreases. So what happens? In the first stage, actually, the dichloromethane accumulates within the rim, and so the rim size increases. But that, beyond a certain point, actually, the volume of the rim is kept constant, but the rim is still stretched by the radial flow. And then, the thickness of the rim decreases as t to the minus n over 2, if t to the n is the power law followed by the radial flow. And because of this, actually, of course, you cannot, let's say you have to adapt the classical Rayleigh plateau theory in order to check whether or not Rayleigh plateau is relevant for what you observe. And so this I already commented on. But in the present system, well, there is an aspect which is quite tricky, which is that since the thickness of the rim is varying over time, there are actually wave numbers which are initially damped because they are on the right part. Suppose at the initial time you are considering some wave numbers here, those they are damped. But since L is decaying over time, actually at some point these wave numbers, they will cross the dashed line here and they will become amplified. Okay? So in order to find the winner, that is the wave number which eventually gets most amplified, actually you have to maximize the cumulated growth rate, and which means actually maximizing this integral here. And so if you do that, actually you end up with the real wave number which gets most amplified. And it turns out that actually some guys have been brave enough in the 1980s to work on such systems. It was not the system I'm considering here, but still they were considering systems in which, let's say, the diameter of the thread is varying over time. And so these two guys are Frankel and Weiss. There are two big GFM papers on this, and these are really, I would say, quite important papers. And so, of course, there is no analytical prediction for the most amplified wave number, but they give the results in the form of these curves here. And actually, well, I will just make the story short and give you the result. But if you consider the proper time at which we can compare our results with these predictions, which is located here, so this red line here, then their theory predicts that actually the most amplified wavelengths normalized by the size of the rim is about 7.5, and actually the observations at the same time give us 7.4. So maybe we were lucky, but maybe there is something in it, and presumably, well, this gives us some confidence that yes, Rayleigh plateau is taking place, but this is a Rayleigh plateau in which there is stretching effect due to the radial flow, but it is Rayleigh plateau. It is still, well, I have to go back. Actually, in this system there are three characteristic time scales. Okay, there is the classical capillary scale, which is here. There is a viscous scale, which has this classical expression, and there is a stretching, which is due to the fact that, of course, the rim is shrinking. Well, the thickness of the rim is shrinking, and the rim is expanding. Okay, but yeah, yes, you're right. Actually, all three time scales are, let's say, fairly small compared to the growth rate. So the quasi-steady approximation is still valid. Yes, thanks. That's an important point too. Okay, that's for the rim. So the conclusion, as far as we can tell it, is that yes, the rim breaks up through Rayleigh plateau instability, which is modified by stretching effects, essentially. So now comes Ratul's question. What makes the system recoil? There are several players. So the rim breaks up and produces drops. These drops spread at the surface of the water. And so for this reason, actually, the water surface around the film gets polluted, let's say. And for this reason, we say that the surface tension drops down to this value, which is half the normal value for water. And this we could verify by inserting a Wilhelmy plate, you see, by pinning a drop in the middle of the petri dish, inserting a Wilhelmy plate, and you see that as soon as you deposit the drop, then there is actually the surface tension dropping by, let's say here, 6 millinewton per meter. And then, of course, when the droplets get away, well, you recover, well, the surface tension re-increases. But clearly, the surface is polluted by the droplets that result from the breakup. So that's one point. And the other point is that, well, you have to keep in mind that there are also surfactants distributed along the oil-water surface. But this surface, well, the area of this surface has expanded by a factor of 5 or 6 during the spreading. And because of this, actually, the local concentration of surfactants has decreased, which makes the surface tension, well, the interfacial tension between oil and water increase. And because of this, actually, in the spreading coefficient, remember that the spreading coefficient is minus. So this guy has decreased, this one has increased, and for this reason, actually, the spreading coefficient gets negative, and the drop, well, the film starts to recoil. Okay, so the rim has break up. well, the film is recoiling, but of course there are still Marangoni stresses at the surface of the film because the film is still evaporating, etc. And so we have the same issue as we had before, that is, there is a non-zero stress at the film surface, there is a zero shear stress on the water surface ahead of the film edge, and so we need a new rim to form in order to accommodate the boundary condition or the transition between the two. And this secondary rim, actually, we are able to see it. Of course, it's much smaller than the primary rim because most of the dichloromethane has faded away, but there is indeed a secondary rim, and in principle, there should be an infinity of rims because each of them is destroyed by the Rayleigh plateau instability, and you need a new one to accommodate the transition, etc. Well, in this case, actually, well, the droplets you see, they are only a few microns in diameter. So with the system, with the observation system we have, we were unable to see the third and fourth, etc. rims. So we only saw the secondary rim, but yes, there is a succession of rims, smaller and smaller rims forming when the drop is recoiling. We have more or less explained expansion, rim breakup, recoil. But you may say, okay, well, the film is recoiling and that's the end of the story. But no, there is chemistry. There is, well, not only, but chemistry plays a role, actually, here. Yeah. Okay. So, as the film recoils, well, the oil-water the area of the oil-water interface is reduced, and again, the concentration of surfactant at that interface increases, and so this guy here decreases now, okay, during the recoil. Also, well, dichloromethane is spread on the water surface, but it evaporates, and it evaporates quite efficiently. So the water surface becomes, let's say, cleaner. So this surface tension re-increases. So we are in a process in which, well, let's say the negative S is becoming less and less negative. But there is a third player, which I don't master at all because this is really chemistry, which is this. So that was shown by Veronique and his co-workers, which is that the surfactant she used, and this is very specific to this surfactant actually, this surfactant uses dichloromethane to solubilize within water. So actually there is some sort of, apparently I didn't see it, there is a sort of micro emulsion forming at the oil-water surface, which helps, let's say, water eat the surfactant, and this again is helping this guy to re-increase. So this is chemistry. As I said, I don't master at all the process, but clearly Veronique showed me curves in which you can see this, and because of this, actually S is able to recovering a positive value at the end of the recoil, and the process for this reason can restart. It's basically half CMC. Yeah, well, of course, if it's beyond CMC, this doesn't happen. Yeah, because beyond CMC, everything is, let's say, full of surfactant, and well, you cannot. You can. Here we are playing with something which is, you say, close to CMC, and this is also what makes this oscillatory system possible. Okay, so let's say that we more or less understand what happens during the first three pulsations. So let me play it again. So this is understood. This is understood. Let's be optimistic. So this is understood, but this seems very specific, and it's so specific that it only happens during the fourth pulsation. So what do we need for pulsation to get this? That was very puzzling. So let's call this, let's say, branches wrinkles. And of course, when I consider these wrinkles, I reminded, well, the nice paper by Peko Soy and John Bush about the tears of wine. And I said, well, there may be some analogy with the tears of wine. Except that, of course, there are many differences, because our geometry is circular, whereas the geometry in the tears of wines is basically planar, but maybe this is not a big difference. A bigger difference is that the origin of the base flow is totally different. In the tears of wine, actually, the flow is driven by thermocapillarity, whereas our flow is driven by basically spreading due to surface tension. And also the evaporation flux in the tears of wine is driven by compositional gradients, whereas our evaporation is driven by temperature gradients. So there are several important differences, but still there are analogies, and indeed we could try something. So the idea was that, okay, we can consider a single wrinkle, not the complete circular system, a single wrinkle, so the spreading flow is going this way. And so suppose there is some disturbance, so some azimuthal disturbance in the height of the film, then the film is thicker here. Keep in mind that, well, the temperature within the film decreases with the altitude. So when the film is thick here, it means that surface tension is larger than on the sides. So there is a stress tending to bring the film here at the place where it is thicker. And so this is basically a potential source of instability. It was shown to be a source of instability in thermocapillary driven film. There is a famous paper in the 80s by Mark Spies and Steve Davis for this reason. And so we tried to, let's say, go one step further into this idea here. And for this, okay, we said, okay, let's consider that there is a spanwise disturbance of velocity within the film. Then this spanwise disturbance generates a quasi-flow in which the spanwise velocity takes this form, actually. So this is basically a quasi-form. And of course, we have to satisfy the boundary condition at the surface. That is, we have, well, the shear stress generated by this velocity has to balance the Marangoni stress, of course. We know actually the distribution of the stress because we know the temperature distribution within the film, and we have the analytical model I showed previously. And so we have a relation between this stress and the variation of the film thickness. And then we can use mass conservation. So mass conservation within the film takes this classical form. And with this, by introducing this expression for the spanwise velocity, we get this nonlinear equation for the film evolution. So you see that it's highly nonlinear because we have h to the cube here and h squared in the last term. So with this, of course, we have to make approximations, and the first of which we made is a long wave approximation, and we suppose the amplitude was small, etc., etc. So if you linearize this horrible equation, you end up with this much more sympathetic equation. And we know the coefficients. We can actually, in principle, we can measure all terms in the coefficient, but we don't know H naught, which is the undisturbed height of the film. In this system, of course, if the prefactor A is positive, then the perturbations which belong to this range of wave numbers, they will be amplified. And for this prefactor to be positive, H naught has to be lower than a critical value, and this critical value is given by this number here. So this is the evaporation flux we measure. This is the exponent with which the film spreads. And of course, this is K0, so this is the most amplified wave number. And so for this reason, because of this expression, we have to conclude that actually the film can develop span-wise instabilities only if the undisturbed thickness is less than a critical value. And so with the exponent, the time exponent we measure for 5 quarters, actually the critical film size below which such a span-wise instability can exist is about 4 micrometers. Yeah, the sinus, yeah, of course. Yeah. Okay, so 4 micrometers, but well, you saw that my first estimate of the film thickness was about 3 micrometers previously. So the maximum growth rate, well, we can calculate it if we know the prefactors A and B. And from this, actually, we can also determine the number of wrinkles. And, well, the number of wrinkles is given by this expression here. And you see that it involves the square root of the film thickness normalized by the critical value. And of course, if you are close to the critical value, it means that you will not observe many wrinkles. So, because during the first 3 pulsations, the film is still thick, quite thick, actually, we don't observe wrinkles. In contrast, during the 4th pulsation, because most dichloromethane has faded away, actually, our estimate for the undisturbed film thickness is only a fraction of a micrometer, about 0.2 micrometers. And for this reason, actually, during the 4th pulsation, this prediction tells us that we should observe up to 7 wrinkles. And 7 wrinkles is not what we observe, because if you look at this, we are rather closer to 25 wrinkles. So the prediction is very poor, but at least it explains why we didn't observe wrinkles during the first 3 pulsations, and we observed them during the 4th. So the reason why the number of wrinkles we observed during the 4th pulsation is too low is not completely clear, but it's true that fully linearizing this wave equation is really very crude. So presumably this is part of the reason why, because, well, it's easy to show that the non-linearity should increase the number of wrinkles by decreasing the wavelengths, actually. So this may be one of the reasons. I was not brave enough for the time being to simulate the nonlinear equation. So this may be part of the explanation. There may be some other parts of the explanation which I still need to discover, but at least we have, let's say, a reasonable explanation to understand why we observe these wrinkles only in the 4th pulsation and not in the first 3 ones. What a surprise! Yes, so of course, linearizing everything in this equation is really very, very crude, but yes, of course it is. 2 minutes, okay. So what happens beyond wrinkle formation? So this is, let's say, more speculative, because this is highly nonlinear. But if you go back to the video I showed you, actually, you see that, well, the wrinkles, at some point, they disintegrate into a series of droplets, of micro droplets, and these droplets even split into 2 series at the tips. So at some point, actually, of course, since the film is thinner in between 2 wrinkles, actually evaporation is more efficient in between wrinkles. So it means that after a certain stage, actually, you essentially have, let's say, capes with dichloromethane, which are separated by bays of pure water, because there is almost no dichloromethane in between 2 wrinkles, and you just have this series of tiny droplets left at the surface. And again, these droplets have their own dynamics. They can coalesce near the tips. Oops. Yes. Well, I will not explain that, but by a simple reasoning, you can understand why actually coalescence occur near the tips. And at the end of the day, actually, you have basically this pattern in which there is still the drop at the middle. You have these tiny droplets splitting at the tip here, and in between there is something which looks at a very thin film here and fresh water along the tips here. So this is the final picture we were able to see. Of course, we can see more than 4 pulsations, but the picture doesn't evolve anymore. We stay with this. Okay, so I will stop there. So you see, this is a long and unfinished story, by the way, but at least I think we were able to rationalize some of the mechanisms that are at play there after almost 5 years. And so after that, we played with the rotating drop I showed at the very beginning, and we are still at work with other parts of the system. Thank you very much.
Long live India and France friendship.